Good afternoon to all of you. Today we are going to cover a very important topic from first year electronics engineering, that is logic gates and non-NOR realization. I am Sulekha Saxena, Assistant Professor EC Department, Ajay Kumar Garg Engineering College, Ghaziabad. So, we will move towards our topic, that is logic gates and non-NOR realization. What are logic gates? Logic gates are basic building block of any digital system. In today's world, all the electronic equipments are based on digital logic, that is 0 or 1, because it is easier to design any circuit based on on-off realization. So, the very smallest unit or the basic unit of any digital system is logic gate, and it expresses the relationship between input and output for a certain logic. The logic gates are broadly classified into three types: basic logic gates, universal logic gates, and other exclusive logic gates. These are also called as exclusive logics. Basic logic gates are of three types: AND gate, OR gate, and NOT gate. Universal logic gates are of two types: NAND gate and NOR gate. And exclusive gates are of two types: XOR and XNOR. So, in overall, there are total 7 types of logic gates. Starting from the very first, that is single input logic gate called as NOT gate. The function of logic is not A, that is A bar or A ka complement. The symbol of this gate is a triangle followed by a circle or notch. It has single input and single output. When the input is low, output is high, or we can say when the input is 0, output is 1, or when the input is 0, 1, output is 0, that is invert. The IC for this logic gate is 7404, and it consists of 6 NOT gates. It's a 14-pin IC with pin number 7 as ground and 14 as plus 5 volt. And there are 6 NOT gates. Pin number 1 is input, 2 is output, 3 is input, 4 is output, and so on. If we talk about the timing diagram, if we supply, check about pin number 1 and 2, if we supply pin 0 at pin 1, we get 1 as output at pin 2. So, the input at pin 1 is reversed and find out at pin 2. Next is AND gate. AND gate is nothing but logical multiplication of two inputs, that is A dot B or B dot A. It follows commutative property, that is A dot B equal to B dot A. It also follows associative property, that is A dot B dot C can be written as we first multiply BC and then multiply it by A, or we first multiply with AB and then multiply by C, the result will be same. 2 input and 3 input, both type of AND gates exist. For 3 input AND gate, function is A dot B dot. We can also write the truth table. If all the inputs are 1, then only the output is 1. If any one of the input is 0, output is 0. So, we write all the 8 combinations 0, 0, 0 to 1, 1, 1, and for all except last combination, any one of the input is 0, so output is 0, and for last combination all the inputs are 1, so output is 1. Similarly, for 2, if we make the truth table for 2 input, then we use 4 combinations 0, 0, 0, 1, 1, 0 and 1, 1. For all the previous 3 inputs, one input is 0, so output is 0, and for last input 1, 1, output is. Now we will go towards the pin diagram and the timing representation. The IC number is 7408. It's a 14-pin IC with pin number 7 as ground and pin number 14 as VCC. 4 AND gates in this IC. Pin number 1, 2 as input, 3 is output, 4, 5 as input, 6 as output, 13, 12 as input, 11 as output, and 9, 10 as input and 8 as output. And now we talk about the timing diagram. We take the input as pin number 1, 2 and output as 3. So if both the inputs are 0, output is 0. If any one input is 0, output is 0. And if both the inputs are 1, then only output is 1. So we can realize the timing diagram by connecting CRO or DSO on the output pin. Moving towards our next gate, that is OR gate. It is also called as logical addition, that is A plus B or B plus A. It also follows commutative property and associative property for 3 input A plus B plus C. If we add last 2 inputs and then the first one, or first 2 and then the last one, result will remain the same. That is, it also follows associative property. If we talk about OR logic, if any one of the inputs is 1, then output is 1. So if we talk about 3 input OR gate, start writing from 0 0 0 to 1 1 1. Only for the first combination all the inputs are 0, so output is 0. For all remaining, one of the inputs is 1, so output is 1. If we write this truth table for 2 input only, we write all the 4 combinations 0 0 0 1 1 0 and 1 1. Then 0 plus 0 0, and for all other combinations one of the input is 1, so output is 1. Now moving towards the pin diagram. The pin diagram of this IC is, pin number of this IC is 7432. It is also a 14 pin IC with pin number 7 as ground, as 14 as plus VCC, that is plus 5 volt. Pin number 1 and 2 as input, 3 as output. Pin number 4, 5 input, 6 output, and so on. And this also IC also consists 4 OR gates. Now again we will see the timing diagram of pin number 1, 2 and 3. So if we give 0 0, the output is 0, and if any one of the input is 1, output is 1, and if both the inputs are 1, then also output is. Moving towards our universal gates. Universal gate is a gate which can be used to implement any Boolean function. That's why these are called universal, because any type of Boolean expression or any other gate can be implemented using universal gate. Universal gates are basically of 2 types, NAND and NOR. Opposite of AND is called NAND and opposite of OR is called as NOR. We will see NOR. As I have told you that opposite of OR gate is NOR gate. So we can simply write this symbol OR plus NOT gate is NOR gate, or the combined symbol is OR with an output notch. Now what about the truth table? In case of OR gate, if any of the one of the input is 1, output is 1, and invert of that is output 0. So for 0 0, OR output is 0, and for all these 1. And if we invert this, then for 0 0 output is 1, and for all other combinations output is 0. This is NOR gate. The IC number for NOR gate is 7402. It is also a 14 pin IC with pin number 7 as ground and pin number 14 as. If we will give the input to the inputs at pin number 2 and 3, the output will be at pin number 1. The input at 5 6, output will be at pin number 4. Input at 8 9, output at 10, input at 11 12, and output at 13. So here also we use 4 NOR gates in this IC. And if we talk about the property, De Morgan theorem can be applied for this IC, that is A plus B ka bar can be opened using De Morgan theorem to write it as A bar dot B bar, and using this logic we can draw the circuit using basic gates A bar dot B bar ka AND gate, that is NOR gate. Now moving towards NAND gate, opposite of AND gate is called as NAND gate. So the symbol can be AND followed by a NOT, which can be simply represented by a notch at the output of AND gate, and the output is reverse of AND operation. For AND gate, if any of the input is 0, output is 0. So if we talk about AND, the output is 0, 0, 0, 1, and if we talk about the invert of this, that 1, 1, 1, 0, and the IC of NAND gate is 7400. It is also a 14 pin IC with pin number 7 as ground and 14 as VCC. It is also a quad NAND gate IC with 1 gate, pin number 1 and 2 as inputs, 3 as output, 4, 5 as input, 6 as output, 13 and 12 as input, 11 as output, and 10 or 9 as input and 8 as. And we can draw the circuit using De Morgan, that is Y is equal to A dot B ka bar. If we open it using our basic De Morgan theorem, then it is A bar plus B bar. So we can simply draw the circuit using basic gates A bar plus B bar. Next are exclusive gates. One is XOR gate. The function of XOR gate is A bar B plus AB bar. It is also called as exclusive OR gate. If only one input is different from other, then the output is 1, else if both the inputs are same, output is 0. So for different inputs, output is 1, and for same inputs, output is 0. That is AB plus A bar B, AB bar plus A bar B. And if we write it using De Morgan theorem, then it is AB bar plus A bar B, which is AB bar plus ka dot A bar B ka bar whole ka bar, that is A bar plus B A plus B ka bar whole ka bar. So this is the way to write it which can further be solved using De Morgan. The IC number for the XOR gate is 7486, and it is again a 14 pin IC with pin number 7 as ground as 14 as VCC. It is also a quad gate IC with pin number 1 and 2 as input, 3 as output, and so on. And the symbol of exclusive OR is an OR gate with a extra slash at the input side. Last is XNOR gate. XOR gate is XNOR gate, that is A bar B plus AB bar ka bar. It can also be solved out to find out that AB plus A bar B bar. And for the output, if both the inputs are same, output is 1, else 0. So for 0, 0 and 1, 1, output is 1. For remaining, output is 0. And if we open it using De Morgan, then we will find out that A plus B bar into A bar plus B. Now we can realize any type of gate using universal gates, that is NAND and NOR. We will start from the first one, that is NAND gate. For NAND gate, the symbol is this. If we design a AND gate, we simply add a NOT gate at the output of NAND gate to get AND gate. If we talk about OR gate, we take two NAND gates as inverter, that is both input common, then the output will be A bar and B bar, and if we do the NAND operation of this output, we get A bar dot B bar ka whole bar, that is A plus B. Now moving towards NOT gate, both the inputs are common, then it is a NOT gate. Moving towards XOR gate. XOR gate is simply implemented using NOR gate. If we talk about this, NAND gate output is itna. If we AND it using first A dot AB bar ka bar, and for the second it is B dot AB bar ka bar, which is A bar dot ka plus AB, and for this one the output is B bar plus AB. If we multiply these inputs again through NAND gate, then it comes out to be A bar plus AB dot B bar plus AB whole ka bar. The obtained expression is A bar B bar plus AB whole ka bar, which is nothing but A bar B plus AB bar, which is XOR gate. So we can simply design a XOR gate using NAND gate, and if we have to design a NOR gate, then we have already designed OR gate and we simply add a NOT gate at the output of OR gate. Now moving towards XNOR gate, this one output is AB bar and this is A bar B bar, the output is A bar B bar whole ka bar. If we AND these two outputs, the final output is AB bar dot A bar B bar ka bar whole ka bar, which is nothing but AB plus A bar B bar, that is X NOR gate. So we can realize all the gates, that is AND gate, OR gate, NOR gate, NOT gate, XOR gate and XNOR gate using one simple gate, that is NAND gate. Similarly, we can realize all the circuits using NOR gate as well. The symbol of NOR gate is this and the equation is A plus B ka bar. If we have to implement a OR gate, we simply add an inverter at the output of inverter, that is both the inputs common in NOR gate at the output of OR gate. If we have to realize AND gate, we will use 2 NOR as a NOT at the input to get A bar B bar. The output will be A bar plus B bar ka bar, that is A dot B, which is nothing but AND gate. Moving towards NAND gate, we add a NOT at the output of AND to get NAND gate. Moving towards NOT gate, we simply common both the inputs to get NOT gate. Now as for exclusive OR, this output is A plus B ka bar, this is A bar B bar and then A bar B bar plus B bar ka whole bar, that is AB. If we add these two, the final output will be AB plus A plus B ka bar whole ka bar, which comes out to be AB bar plus ka dot A plus B. If we open this circuit, this is A bar plus B bar and A plus B, that is A bar B plus A B bar, which is XOR gate. And for XNOR gate, we use the same logic, A plus B ka bar. When first it is multiplied with A using NOR gate, the output comes out to be A plus a plus b के बार का होल बार, that is a bar dot a plus b, which is nothing but a bar b. And similarly for the second, the output is b plus a plus b का बार whole का बार, and if we add these two outputs we get a bar b plus a b bar का bar, which comes out to be a bar b out to be ab plus a bar b bar, that is x NOR gate. So we can implement all the gates, that is NOR, OR, NAND and exclusive OR and exclusive NOR gates using universal gates. Now we talk about the number of gates used to implement these circuits. Using NAND gate, if we implement NOT, we require only one. For AND gate we require two, for OR we require 3, for XOR 4 and XNOR 5. Similarly, for using NOR gate, 1 for NOT gate, 3 for NAND, 2 for NOR, 5 for XOR and 4 for XNOR. We can count this from here. For OR gate we require 2, for AND gate we require 3, for NAND gate we require 4 IC, which is not written here. Then for NOT gate only 1. For XOR we require 2, 3, 4, 5, and for XNOR 4. So 5 and 4. Similarly, using NAND gate we require for AND 2 or 3, NOR 4, NOT 1, XOR 4 and XNOR 5, which is written here. Now what are the possible logic operations? For two inputs with all the possible combinations 0, 0, 0, 1, 1, 0, 1, 1. F0 means all the outputs are 0. F1 for NOR combination. Then this is NOT combination, this is NOT Y, this is NAND, and so we can write all different type of possible combinations. That is, if there are two variables with 4 combinations, then we can have 2 to the power 4 possible functions with n variables. That is, we can in general write, we can have 2 to the power n possible functions with n variables. And these are the different identities which are used to minimize those functions. We can solve Boolean equation using these identities. The first one is identity theorem. That is, if we add 0 to any variable, it will remain unchanged, and if we multiply with 1, the equation will remain unchanged. Then null equation, if we add 1 to any equation, output will be 1, and if we multiply with 0, output will be 0. Then complementary theorem, that is variable plus complement equal to 1 and variable into complement equal to 0. Then idempotency theorem says if two values are added, the output will be same, and for they are multiplied, then also output will be same. Involution theorem says that x complement, and if we again complement, we will get the same variable. Commutative theorem states that x plus y equal to y plus x and x dot y equal to y dot x. Associative states that x plus y plus z equal to y plus z, and then we add x. The same theorem can be used with dot also, that is x dot y then dot z equal to y dot z then dot x. Distributive theorem can be written as x dot y plus z equal to x dot y plus x dot z, and x plus yz can be written as x plus y dot x plus z. That is, absorption theorem states that x plus dot y equal to x. We can simply write it as x in bracket 1 plus y and 1 plus y equal to 1. So, it is x. Similarly, x dot x plus y. It can be written as x plus xy, which can again be equal to x. Similarly, adsorption theorem, x plus x bar into y can be written as x plus y. We can simply derive it x 1 plus y plus x bar y, x plus y common x plus x bar, which can be written as 1. So, the equation comes out to be x plus y. Similarly, x dot x bar plus y is equal to xy. If we write y plus xy bar is equal to x, and x plus y into x plus y bar is also equal to x. Moving towards consensus theorem, if we write xy plus x bar z plus yz, it comes out to be xy plus x bar z. For this, to derive this, we simply multiply yz with other two values. So, xy plus x bar z plus yz x plus x bar, and we write xy as common between this and this 1 plus z plus x bar z common 1 plus in this and this 1 plus y. So, 1 plus z and 1 plus y equal to 1. So, the equation comes out to be xy plus x bar. Similarly, we can derive x plus y, x bar plus z, y plus z equal to x plus y and x plus bar plus z. And last but very important, that is De Morgan's theorem. It is used to convert AND to OR and OR to AND operation. We can simply write it as, if all the variables are added, the equation is complemented. All the variables will be complemented and plus is replaced by dot and vice versa. So, x1 is replaced by x1 bar, x2 as x2 bar and xn as xn bar, and plus is replaced by dot. Or we can simply say that for two variables a plus b ka bar, that is a bar plus dot b bar. So, De Morgan is used to convert any addition equation to product equation and vice versa. Similarly, we write to plus, then a dot b ka bar is equal to a bar plus b bar. Next is duality theorem, which is nothing but statement of De Morgan. Duality was also used to convert dot to plus and plus to dot. It states that if we replace any variable with its complement and replace dot by plus and plus by dot, the obtained expression is dual of original expression. To solve any equation, the order of preference will be first parenthesis, then not, then and, then or. So, in this way, Boolean functions are generally expressed in terms of logical variables, and we can write any function in terms of SOP or POS representation. What is SOP? In SOP, a variable is represented by 1, whereas variable complement is represented by 0, and each product term is sum up to get the final form. Whereas in POS, the variable is represented by 0 and variable complement is represented by 1, and each term is in some form and overall is the product of some terms. So, we will further use SOP and POS representation to solve Boolean expression in our next lecture. Thank you all.